Assalamualaikum warahmatullahi wabarakatuh. Salam UTM Sarjana Bangsa, Salam Malaysia Madani, and welcome to our video. So, for this video, we'll be talking about our assignment, which is focused on us designing a circuit which consists of a bandstop filter to address the issue of the 50 Hz power line interference in the ECG signals. In this video, we'll be looking at the introduction for our assignment, which consists of the paper overview, and also the applications and also the problems that are faced with the ECG, and we'll be also analyzing the application requirements. After that, we'll be looking into its problem statement, and next, we'll be looking at the methodology. So, what methods are we going to use into building up or designing our bandstop filter? And once we already designed and also created our bandstop filter, we'll be doing a simulation and we'll be presenting the results that we have found. And lastly, we'll be doing our conclusion for our assignment. Now, for our group members. So, my group consists of Iskandar, Aiman Saif, Zaini, and also myself, Taufik. So now, for the introduction. So, the electrocardiogram, also known as ECG, is a device that measures the electrical activities in the heart. So its signals are essential for diagnosing heart conditions. But they are often affected by power line interference, which is 50 Hz, which can distort their signals, such as like the P wave and also the QRS complex. So to remove this narrowband noise without harming the rest of the signal, bandstop filters are very needed. So we selected a research paper by Hilda Afifa and Nicodemus Ritadian in 2020, and they present a compact and efficient end-pass bandstop filter design for suppressing 50 Hz noise in biomedical signals. The filter achieves high attenuation while preserving ECG signal quality, making it suitable for portable or lower power medical devices.
Hi, Assalamualaikum. I'm Muhammad Iskandar. I will explain about the paper overview. So for the first one is the biomedical context. Power line interference is a major contaminant in biomedical signal equation, particularly ECG and EEG, degrading diagnostic accuracy. The paper tackles this pervasive issue through hardware-level filtering. For the next one, filter architecture. Introduce an end-pass notch filter designed tailored for narrowband rejection of 50 or 60 Hz interference. Comprise multiple switch capacitor path and optimized switch resistance for high attenuation. Demonstrates more than 40 decibel notch depth while minimizing component count and power draw. Design and simulation. Simulated using artificial ECG data contaminated with hum noise at 50 Hz or 60 Hz. Tests across varying sampling frequencies. Results show robust hum suppression without signal distortion, even up to 60 Hz. So for the application and problem, the electrocardiogram ECG is a non-invasive diagnostic tool used to monitor electrical activity of the heart. It plays a crucial role in identifying heart rhythm disorders, detecting heart attacks, and evaluating overall cardiac function. ECG signals are typically very low in amplitude, ranging from 0.5 millivolt to 5 millivolt, and contain important features such as the P wave, QRS complex, and T wave. Accurate detection and analysis of these features are essential for proper medical diagnosis. However, ECG signals are often contaminated by power line interference, we call as PLI, which is a narrowband noise at 50 Hz or 60 Hz in some countries. This interference is caused by surrounding electrical equipment, lighting, and power supply systems. Since 50 Hz falls within the frequency range of the ECG signal itself, typically 0.05 Hz to 100 Hz, it can significantly distort the signal, masking critical waveforms and reducing diagnostic accuracy. And for the last part, analyze application requirements. So for the first one, application context. The problem we address here is ECG signals are often contaminated by power line interference, also known as hum noise, typically at 50 Hz in most countries, including Malaysia, and 60 Hz in North America and some parts of Asia. While filtering is needed, the 50 or 60 Hz is interference overlaps with the ECG signal, bandwidth 0.05 until 100 Hz, making it hard to detect critical features like P wave, QRS complex, and T wave. Removing this noise without distorting the ECG waveform is critical for clinical diagnosis. For the next one is cut-off frequencies. The bandstop, or we call as notch filter, is centered at 50 Hz or 60 Hz depending on the region. For this research, center frequency is 60 Hz. Is 50 Hz. Lower cut frequency approximately 49 Hz. Upper cut-off frequency approximately 51 Hz. So the cut-off frequency for the lower cut-off is 49 Hz, and for the high cut-off is 51 Hz. For the third one, stop band range. The stop band is the narrow frequency range where the filter significantly attenuates the signal. In this case, for the first one, stop band 49 until 51 Hz, and the next one is this range targets only the 50 Hz interference to avoid fighting nearby ECG signals components. The filter achieves a deep notch high attenuation at the center of this stop band. And the last but not least, roll-off requirements. Roll-off refers to how sharply the filter attenuates frequency after the pass band as it approaches the stop band. In this application, the notch filter is designed for narrow band rejection, so sharp roll-off is essential to remove 50 Hz noise effectively and preserve important neighboring ECG frequency components such as those around 40 until 45 Hz or 50 until 55 until 60 Hz. The performance from the paper. The filter achieved a notch depth more than 40 dB at 50 Hz, minimal transition bandwidth, ensuring easy ECG waveform integrity.
Alright, for problem statement, power line interferes in ECG signals, which means ECG signals are vulnerable to noise, especially from 50 Hz to power line interference, which is PLI. So PLI overlaps with ECG frequency range from 0.05 until 100 Hz. This can distort important waveform components P wave, QRL complex, and T wave. This interference may lead into misdiagnosis, especially in portable and clinical monitors. So Lefko's the research paper proposed a digital subtraction, but this project focused on an analog solution. Now for the next part, we have filter objective and approach, which is suppress 50 Hz interference from ECG signal, preserve ECG waveform integrity, which is QRS and T wave, analog implementation suitable for the real-time and embedded ECG system, and it is used multiple feedback, which is MFB topology for narrowband filtering. Next we have Butterworth response selection. Why we choose the Butterworth? Because it is flat pass band, which is minimal distortion to ECG, no ripples, adequate roll-off, negative 40 dB per decade, and commonly used in biomedical instrumentation. Next we have a second order filter. Why we choose second order filter? Which is it is sufficient attenuation, which is from 50 dB at 50 Hz, fewer components, which is ideal for compact and low power device, easier to build and tune compared to the higher order filters, and minimize phase distortion and complexity. And MFB bandstop filter use 1 ohm amp, 2 capacitors, and a multiple resistors, which the advantage is high Q factor, sharp attenuation, stable and compact, and preferred for narrowband and analog filtering. Alright, next for the component selection and calculation. The target frequency at F0 is 50 Hz, which is we assume the C1 and C2 is 0.33 microfrequency. We calculate the R using 1/2 pi RC, which we will get our R is 9.65 kilo ohm. And for the final value of component, so we will get R1 equal to R2, which is 9.6 kilo, and C1 equal to C2, which is 0.33 microfrequency, and the quality factor is 5. So the supply voltage and ohm amp requirement is ohm amp. We have LM741, TL072, or LF351. So dual supply from positive to minus 5 volt to 12 volt recommend, and single supply requires virtual ground at midpoint, example 6 volt, and ohm amp requirement, low noise and good bandwidth and suitable for biomedical signal, which is for the ECG, and the expected filter performance, which have center frequency 50 Hz, stop band range which is around 49 to 51 Hz, attenuation rate from 40 to 60 dB, roll off 40 dB per decade, and passband ripple, which is less than 3 dB, and quality factor, which is 5, and maintains ECG clarity while rejecting 50 Hz noise.
Move on to circuit diagram. As you can see here, there are two resistor and two capacitor connected in series. Between the capacitor, there are one resistor which is half of the R1 and R2 value, and then the capacitor between the resistor is twice the value of C1 and C2 value. And then we have the RF, which is the same value as R1 and R2, and then the RC circuit connected to the negative value of op-amp. And then we use Bob plotter to determine the graph, which is the input we put in front of the circuit and the output at the Vout. Here is the result. It shows that the Bob plot has a sharp edge when the frequency is at 49.36 Hz, which is almost the same as 50 Hz. The attenuation is equal to approximately negative 51.33 decibel. The attenuation, which is very strong. Thus, this is indicate the filter was successfully rejecting signal around 50 Hz. The circuit is functioning as second order band stop notch filter. Next, for the second result, shows that the sharp edge at the positive side, which is the top notch of the Bob plot. The simulation result indicates that the circuit functions as a narrow band pass filter. It achieves a maximum gain of approximately 65.9 decibel at a center frequency of around 9.773 kHz, demonstrating that the filter is sharply turned into the specific requirement.
To sum up our assignment, our project focused on designing and simulating a bandstop filter, specifically to address the issue of the 50 Hz power line interference in the ECG signals. So this type of interference is very common in the medical diagnostics and can distort critical waveforms. So we designed a circuit that counters these issues. So first of all, for the circuit design, we designed a 20-notch filter which effectively removed the 50 Hz power line interference from the ECG signals, which is crucial for getting the most accurate medical diagnosis. So next, for our simulation results, our multisim confirmed that strong attenuation at 49.36 Hz with a depth of negative 51.33 dB, proving that our design has met its frequency rejection goals. So next, we have a clean ECG output. So the filter preserves key ECG features such as the P wave, QRS complex, and also the T wave, ensuring no distortion in diagnostic components. And lastly, we have real-time suitability. So our circuit is very simple, low power and reliable, making it highly suitable for real-time biomedical applications such as the wearable health monitors and ECG machines. So now we are at the end of the video. I hope that our circuit has satisfied the requirements for this assignment, and hopefully we can get A+ for this subject. So that's all from us. Thank you.